Welcome to the Explainer. Today, we're diving headfirst into the ultimate logistical miracle that actually makes the entire internet work, the transport layer. Whether you're grinding away at your CCNA, studying cybersecurity, developing software, managing systems, or you're just a university student trying to make sense of network protocols, you are absolutely in the right place. We are going to decode exactly how your data moves across the globe without turning into a complete chaotic mess.
Think about it for a second. You fire off a quick hello on WhatsApp and it feels instantaneous, right? Totally seamless. But beneath the surface, there is a massive, highly coordinated sorting operation going on. Your data is being chopped up into tiny pieces, addressed, checked for errors, converted into electrical signals, and literally blasted across the world to be reassembled perfectly on your friend's screen. So, how does your computer know to prioritize the instant reaction of a multiplayer game over, say, the slow, steady download of a massive video file? Well, the secret lies in one very specific layer of our internet architecture.
So here's our roadmap for today. 1. The delivery manager. 2. The TCP versus UDP showdown. 3. The three-way handshake. 4. Traffic cops, also known as ports. 5. Flow and congestion control. And finally, 6. Layer 4 in the wild. Let's get into it.
Section 1. The delivery manager. First things first, let's establish exactly where the transport layer actually lives in the grand scheme of your network.
To really understand networks, we use the OSI model. It's the classic 7-layer framework that standardizes how our devices talk to each other. Up at the very top, layer 7, you've got the application layer. That's your web browser, your email client. Down at the bottom, layer 1 is the physical layer, the literal copper cables, fiber optics, and Wi-Fi signals. But right in the sweet spot, right in the middle, is layer 4, the transport layer. It sits perfectly between the software session managers up top and the hardworking IP network routers below. It's literally the bridge between the apps you use and the physical network carrying your data.
So what's its actual technical day job? Basically, the transport layer is responsible for reliable end-to-end data delivery. It takes a massive chunk of data from your application, say a 20-megabyte video file, and it breaks it down into smaller, much more manageable pieces called segments. It even tacks on a checksum to verify that the data hasn't been corrupted. It ensures these segments travel safely from the source device all the way to the destination device, handling all the multiplexing and flow control along the way. Honestly, without layer 4, our data would just be a disorganized flood.
Section 2. The TCP versus UDP showdown. Let's see how this works in practice. To wrap your head around this intuitively, I absolutely love this analogy. Think of our first protocol, TCP, as a registered courier. When they drop off a package, they demand a signature. If you aren't home, they come back and they try again until that package is 100% secured in your hands. Now, the second protocol, UDP, is more like a live TV or radio broadcast. It just keeps transmitting out into the void. It really doesn't care if you've tuned in or if your TV flickered. It just keeps pushing that signal out as fast as humanly possible.
And when we look under the hood at their strict technical specs, it totally makes sense why they act this way. TCP, or Transmission Control Protocol, is obsessively focused on reliability. It's connection-oriented, it constantly checks for errors, and it guarantees that your segments arrive in the exact right order. But because of all that constant double-checking, it's inherently slower. UDP, or User Datagram Protocol, just sheds all that extra overhead. No connection, zero delivery guarantees. If a packet drops, oh well, it's gone forever. But because it skips all that paperwork, it is insanely fast.
And this brilliantly illustrates why we literally need both of them every single day. When you're loading a secure website over HTTPS, sending a critical email, or downloading a file, you have to use TCP. If even one single byte of a file goes missing, the whole thing is corrupted. You need 100% data integrity. But if you're playing a fast-paced online shooter, watching a live stream, or you're on a Zoom call, that's all UDP. In a voice call, if a tiny millisecond of audio drops, you just hear a little blip. If the protocol paused the entire call to go back and fetch that one missing blip, your conversation would lag terribly. UDP prioritizes instant reaction times over perfection.
Section 3. The three-way handshake. This is all about establishing trust.
So we know TCP is highly reliable, but here is the kicker. Before it sends a single byte of user data, it has to establish trust. Think about the logistics for a second. You're sitting in New York, the server you want is in Germany. How do these two machines agree to dedicate resources to each other and sync up over thousands of miles of deep-sea cables and random routers? Well, they do it through what is famously called the TCP Three-Way Handshake. It's a literal three-step digital conversation. Step 1, the client sends a SYN packet, which stands for synchronize. It's basically knocking on the door saying, "Hello, I'd like to open a connection." Step 2, the server gets this and replies with a SYN-ACK, or synchronize acknowledge. That's the server saying, "I got your request and I'm ready on my end." Step 3, the client replies with an ACK, or acknowledgement, saying, "Awesome, got your confirmation, let's do this." Only after that specific handshake is complete does the actual data start flowing. And because of that handshake, both sides are now completely synced up. They can assign sequence numbers to track every single segment of data. So, if the sender fires off segment number 5, it pauses and waits for an ACK from the receiver saying, "Yep, I got number 5. Now, if a segment gets lost in transit, maybe a router somewhere randomly got overwhelmed, the sender just notices that the ACK never arrived, and its internal timer runs out. When that happens, boom, the sender automatically retransmits that specific segment. That right there is the absolute magic of TCP's reliability.
Section 4. Traffic cops, or port numbers. Let's see how your computer prevents all this incoming data from just turning into absolute chaos.
To intuitively wrap your head around this, think of network addressing like the Postal Service. The IP address from Layer 3 gets your data to the correct apartment building. The MAC address from Layer 2 gets the data to the specific door number of the exact computer. But once that data gets inside the computer, who is it actually for? Is it for your web browser, your email app, Spotify? The port number identifies the exact application or the specific person you are trying to talk to inside that computer.
Technically speaking, when you smash an IP address and a port number together, you create what's called a socket. So an example would be 192.168.1.5 on port 443. And this socket system is exactly what enables something called multiplexing. Multiplexing is the reason your computer can run Google Chrome, Discord, and an online game all at the exact same time on the exact same Wi-Fi connection without the game data accidentally popping up as raw code in your web browser. The transport layer demultiplexes the incoming data, looks at those port numbers, and flawlessly sorts the traffic to the correct apps.
And to keep things from being a total free-for-all, the internet relies on well-known standard ports. These act as the dedicated traffic lanes for everything we do online. When you browse an older, unencrypted website using HTTP, your browser automatically aims for port 80. For modern secure web traffic, HTTPS, it uses port 443. File transfers use port 21. Secure remote access via SSH uses 22. And when your computer needs to translate a website name into an IP address using DNS, it fires off a quick UDP request to port 53.
Section 5, Flow and Congestion Control. The really crucial point here is that Layer 4 doesn't just deliver data, it manages the entire internet's traffic jams.
Imagine a beefy, high-speed server just blasting gigabytes of data at an old, slow smartphone. If the server just sends data at its absolute maximum speed, the phone's memory buffer is going to overflow instantly and it'll just drop the packets. Or on a larger scale, imagine millions of devices suddenly flooding a major network router at the exact same time. How does the transport layer step in and prevent everything from just crashing?
Well, to prevent widespread disaster, TCP uses two vital but completely different mechanisms. First up is flow control, which protects the specific receiver. It uses a clever mechanism called a sliding window. The slow smartphone literally communicates back to the fast server saying, "Hey, my window size is pretty small right now. Only send me a few segments at a time." As the phone processes the data, that window slides forward. Second is congestion control, which protects the entire network infrastructure. TCP uses algorithms like slow start. It starts sending data slowly, testing the network's capacity, and only ramps up the speed if no packets are getting lost along the way.
Bringing this back to reality for a second, without these specific Layer 4 throttling mechanisms, our modern web simply would not function. If every device out there just greedily sent data as fast as its physical cable allowed, the central routers of the internet would suffer constant traffic jams, massive packet loss, and total gridlock. The transport layer is quietly acting as the internet's automated traffic controller, constantly adjusting speeds second by second.
Section 6, Layer 4 in the wild. Let's wrap this up by looking at how IT professionals actually use this knowledge in the real world.
Let's say a user complains they can't access a critical website. A good network engineer or sysadmin is going to troubleshoot using the OSI model, layer by layer. First, Layer 1, Is the physical cable actually plugged in? Layer 2 is the MAC address communicating with the local switch. Layer 3 is the IP address routing correctly. Then they hit Layer 4, the transport layer. They'll ask, wait, is port 443 actually open on our firewall, or is it blocking the TCP traffic? Finally, they check Layer 7. Is the DNS application actually resolving the website name? Really understanding Layer 4 allows you to pinpoint exactly where the communication is breaking down.
So, we've seen how the transport layer manages the incredible complexity of the Internet, relying on the careful, verified delivery of TCP and the raw, uninhibited speed of UDP. But as we move into a crazy new era of virtual reality, real-time remote surgery, and instant global communication, network engineers are constantly innovating. If TCP gives us absolute reliability and UDP gives us unmatched speed, what are the transport protocols of the future going to look like to finally give us both? It's a pretty fascinating space to watch. Thanks for joining me for this explainer. Keep exploring, and I'll catch you in the next one.